Okay. So today we are going to start looking at the problem we have to solve, that you will have to solve, which is starting with the EPFL building stock and characterizing the EPFL building stock in order to be able to calculate what will be the demand that the building stock needs in order to calculate what will be the energy system that will be then afterwards used to supply this demand. So it means that we are going to look at the whole site of EPFL with a lot of buildings, like you see here, and some of the buildings are indeed connected to different types of heat distribution systems. So you have the old part. The old part is the part that is the part that is here in orange. That is, in fact, the part that is heated with high temperature. So those are all the old buildings, in fact. And then the yellow part, which is heated with a lower temperature district heating system. So it means that we have two district heating systems. And this is mainly because once they have decided to develop the building stock, they realized that the lower the temperature for the heating system, the better is the coefficient of performance of the heat pump. And so if you want to be more efficient, then you have to reduce the temperatures in the building. And so the new part, which is here, in fact, is situated or connected to a lower temperature district heating network. And the value that you can see here, so the maximum temperature here and here, in fact, temperatures that are the design temperature. So it means they have decided that there was a minimum temperature at which the buildings will need to be heated. So let's say -10, for example. And considering them not -10, they have calculated the heat exchangers, the heat distribution system that you have in the radiators here, in such a way that they will be big enough to be heated when the temperature is the maximum temperature that is given here. Okay? Which indeed is going to give you a degree of freedom. You can also decide to optimize the temperature profile. If the temperature outside is higher than the -10, then it's not necessarily needed to feed the building with the 50 degrees C. Okay? Because you have a given area, heat exchange area. The temperature is lower, the heat load, the temperature is higher, so the heat load to be supplied is smaller, the same area is available, and therefore you can reduce the temperature difference. Okay? And so it means that you will have to optimize or to define the best temperatures as a function of the temperature outside. Okay, so now let's go in the buildings to see what is going to happen so that we will be able to define what are the needs of the different buildings. Okay, so if now I'm going down and I'm going to look at one building, okay, so I'm going to have a look on what are the energy needs of a given building. Okay. And if I'm looking at what it means, the energy needs of a building, I'm going to realize that on the building, on one side, on one hand, here, we can see that the building is cooled down. So it means that there is a flow of cold water entering in the system, and this is the cooling system. Okay, that is connected to the building. In fact, I'm simplifying a lot because there are a lot of radiators everywhere, but okay, let's consider that we have a connection to the cooling district heating system. And Then we will have, for each of the building, connections to the heating system, which is the red part here. So the heating system here. And what we can see is that the heating system is characterized by, in fact, two temperatures. So I will name it the supply and the return temperature. Okay? And this district system is going to, and this is for the distribution system B. Okay? So it means that now I have D being the heating, another D will be the cooling, okay? So we'll have a collection of distribution systems connected. Now I have to see what are those, how is the heat that is distributed used in the building. And what I can see is that the heat is going to be used, on the one hand, here, to supply some heat by convection in radiators, okay? It's also possible that the district heating system is going to be used in order to produce the hot water. But if you are smart, you will see that in EPFL, it's really rare to find hot water in all the... They have changed everything, in fact. 10 years ago, they had decided that the hot water is not always needed, so you can do a lot of things with cold water, and so they have removed all the hot water supply. Okay, but nevertheless, so you could consider that you have a connection for producing the hot water. And then there is another connection here, which is related to the ventilation. So the ventilation is, in fact, the fact that we have to renew the air. So you are producing carbon dioxide and water when you live, okay? And this, and you need oxygen. So it means that we have to be sure that you receive the oxygen that you need, so that you are really efficient when you listen to me, okay? In such a way that, and for doing this, so when we are in a heating period, so not like today because apparently the windows are open, but at least typically there is a ventilation system that is going to renew the air. So it means that it's a system that is in fact taking the air out of the building and taking the air, so by pressure difference it's taking the air from outside, okay? And this air is, in some buildings at least, not all, is in fact preheated. Here it's a heat recovery unit, here, which is going to do an exchange between the air that is in the building, that needs to go out, it's a depleted air, and the fresh air that is entering. And the fresh air that is entering is preheated in this heat exchanger. And of course, there will be a temperature difference here, especially because there is a difference in flow, because there are also leakage in the building. So it means that part of the, I should have added, I'm going to do it directly. I should have added here a flow of air coming from outside that are all the leakage, so the windows that are open, the doors that are open. You have seen that in EPFL there are always two doors when you enter somewhere, and it's also to reduce the amount of leakage. Okay? Otherwise, if you are sucking the air out of the building, then you are also asking the air to enter the building, and it creates burden, in fact. Okay, so the idea is to limit the amount of air coming via the leakage, so that at the end the whole amount of air will enter the system via the pipe that is here. Okay, and this is coming from outside. Huh? Okay, so there is a preheating, and then once you have preheated, then you will finish the heating by heating the air so that we can blow air at a higher temperature inside the building. this is the connection to the heat distribution grid. Okay. At the same time, we can see that we have as well an electrical grid. Okay, the electrical grid that is going to operate the computers, operate the lights the people need. Okay, and we can also consider, and it depends on the implementation, but we can also consider that we have PV panels that are on the roof. So those are here the PV panels, and those PV panels are going to supply electricity that can be used in the system. And what are the usage? So it's the lights, it's the appliance, and it's here the blowers as well. So if I need to blow the air, I need electricity. Okay, which means that at the end I will have a connections to the electrical grid. Okay, so now if I have to define what the system, the energy system has to characterize or to supply, then I need to be able to calculate what will be the flows that are needed in the different subsystems here, which means that I will have to calculate what I am I will have to calculate for each of the demand or the distribution grid for each time. So I treat each hour of the day. What is the heat that needs to be supplied by this distribution system? Okay, and I will name it QB for B for building, D for distribution system, and T for time. Okay. And at the same time, I will have to define the electricity amount that I will define as being E, B for building, T for temperature, for time, sorry, which is indeed the sum of what the light is giving to us, the PV panels that can produce electricity also, the appliance and the blowers. Okay, so this is what I need to characterize if I want to be able to calculate the needs of the full system. And if now I'm looking at the full system, it will be a combination of buildings. So now I will have a list of buildings. So those ones are the ones that I was describing before. Okay, that are fed on with different distribution systems. Okay, and that will be fed by an energy conversion system. So it means that now here I will have to make the sum. So this will be the sum of all the heat load on each building, so over the building, okay, of each building at a given, on a different distribution system at a given time, okay, to know what is the amount of heat that needs to be distributed at a given time in a given building, in a given distribution system. Okay, which means that if I'm making the sum, then I will know what is needed here, here, and here. Okay. And now I'm going to look at the way I'm going to supply those amounts, and I'm going to therefore look at a heat pump that will perhaps that will use the water from the lake. And so this is the lake. It is here. And I'm going to take the energy from the lake in order to, for example, supply the heat to this distribution system here via the consumption of a given amount of electricity that I will have to connect on the electrical grid. Okay. The same for another heat pump that is perhaps going to produce the cold or use the cold directly, so it depends here if I'm making a connection or not, okay? And it can supply the heat to the lower temperature system, okay? And at the end, I will have to make here, at this level, the sum of all the electricity consumptions that I will have. I will have to sum the contributions of each of the heat pump in my system to the sum of all the demands of all the buildings in my system, okay? And then I will realize that at least today we have also a gas turbine that is here. So the gas turbine is going to produce electricity that can be then used to reduce the amount that we are going to import from the grid. That is going to consume fuel, the fuel that is going to enter here, and that is going to supply heat that can then be connected to a given grid, so a distribution system. Okay? So now if I'm looking at all those elements, I'm going to make calculations. So the first thing that I'm going to do is that I'm going to make the sum, so I'm going to take, I'm going to calculate the amount, okay, the amount that is needed for each of the grid. And I can even translate it as the flow that is needed in each of the grids. So what I have done here is, on the top here I have the balance, so the amount of heat, this one is the amount of heat, this is the amount of heat that is needed in a distribution system at a given time, which is the sum. And if I know the amount of heat, which is this one, then I can calculate the flow of water by, if I know the temperature difference between the supply and the return in the distribution system. Okay? And those are imposed at the level of the production side. So at the production side, I'm going to impose a supply temperature for each of the distribution system. I'm going to impose a return, or at least an expected return, because in reality it's the result of the exchange with the building. And knowing the heat capacity of the distribution system, I will be able to calculate the mass flow in the distribution system. If I know the mass flow in reality, I can also calculate the amount of electricity that is needed by the pumps to circulate the water. Okay, but in this case, I would need as well to know what is the pressure drop that is a function of the amount of water that is distributed. Okay, that means that I could add details in my model. But by using this, then I will be able to then write a balance, and the balance is will be expressed by this kind of equation here, in which I'm going to say, okay, I know how much heat needs to be distributed by the distribution system D at time t. Now I'm going to decide at which level I'm going to use which utility system, so for example, which heat pump, that will supply a given amount of heat. So the given amount of heat is here. That will be multiplied by the level of usage, which is the FUT. So it means that now I have a system that is going to consume a certain amount to produce a certain amount of heat. So this is what is the Q that is here, is what is delivered, for example, in this one, or what is delivered in this one, or what is delivered in this one. Okay? And by doing this, then I will be able to know how much heat is supplied by a certain level of usage of one of the different utility systems. So for example, here I will have, let's U, that is heat pump low temperature, and I will have the Q that is distributed by this one that is equal to the flow of this U at the time T times a specific heat that is distributed by this unit. Okay? And if now I know the link between the flow here, which is the electricity that is consumed by U at time T. Okay, so it means if I know the ratio between the Q ut and the E ut, and this is something that we name the coefficient of performance of the unit at time T, U at time T, then I will calculate E as being equal to Q times the COP of UT. It's the reverse is divided by the COP. Okay? So now it means that I will be able to calculate the amount of electricity that is needed by the unit U at time T, and of course I will have here a balance, and this will be the electricity balance, which is going to say that the electricity that we are going to import is equal to the sum of the electricity that is needed for all the buildings at time T, plus the sum over all the units, okay, of the electricity that is used or needed in each of the unit. And of course, when I will be here, this will be a contributor, so it will be a negative consumption. Okay? It means that this one will be, this is the gas turbine at time T, and this will be negative. But it will have an impact, because then there is an M fuel here, multiplied by the LHV, multiplied by the efficiency of the gas turbine, that will give me the EGT at time T. Okay? So this is the way I will calculate the contribution of the electrical consumption of the gas turbine, which will allow me in reality to calculate the fuel consumption. And once I have the fuel consumption, then I will have the cost of operating at time T. And the same when I will go here, and when I will know the amount of electricity that I need, then I will have the cost of the electricity that is that I need to buy to feed my system. So the conclusion of it is that you can see that we have to define first the demands of each of the buildings. From the demands of each of the building in terms of heat and in terms of electricity, so the EBT here. Huh? From the sum, I will know what the energy system needs to be to supply in form of heat and needs in form of electricity. Then I will activate the different units that are here. So that produce heat or cold at different temperatures. Okay? I will be, by using a balance, able to calculate what is the amount of flow that I need from the lake. If I know the CP of water and the T supply and return of the lake. Okay, so it means that I will know how much I have to pay to pump the water from the lake as well. Okay? I will make a balance, and then I will know what are all the resources that I need to buy. Okay? Questions? Seems to be clear to all of you? Okay, so on the website you will have, in fact, the problem description, in which you will have the list of all the equations that I have explained. So how we calculate the CP, how we calculate the energy balances in the system, how we write the electricity balance, the resources balances. Okay? And you will have the definition of all the sets on which we are going to work, the set of the technologies, the sets of the time frame that you are going to consider, the set of resources that you will have, the set of buildings that we will have to supply, and the set of the distribution systems. So there will be a complete definition of all the variables, and this afternoon, together with the assistant, you are going to receive the model, and Alessio is going to explain how it works. But the full description is given. Okay? Right, so in French we say yaka. Okay, so you just have to. Okay. And where do you see the difficulty now? I'm going back to my problem here. So where do you see the major difficulty now? I give you the equations, you are happy.
Characterize each building for knowing what's the temperature, inlet temperature.
So now the problem is that we have to be able to characterize each of the building of EPFL. So I'm going back here. So this is a challenge. So you see that there is a lot of buildings, okay, that have not been constructed at the same time, so they have different quality, okay, and then they need to be fed, or we have to characterize how much heat and electricity they need, each one. Okay, so how would you do this? Let's assume that you are an engineer and your boss says, okay, give me the answer for EPFL. So how do you characterize the buildings of EPFL? Yeah.
I would sort them by building construction time, because they have the same losses.
Okay, so it's interesting. So he's going to, because it's a nice approach. So what you say is that I'm going to rank the buildings with time, because a priori the architects at a given time have applied the same rules. And most probably they will have the same quality. And if you, and this is correct, so if you go through EPFL, you will see that there are different types of architecture and different types of construction materials. So the one we can see here, for example, the metallic facades are from the same period, so the initial period 50 years ago. Okay? So it means that it allows us to have an idea. Now, how do you characterize the losses?
Refer to an architect.
Yeah, this is. In fact, there are. So let's say refer to an architect. So I take this as one option. So I'm going to write it here. So. And how do you think that the architect will give you an answer?
It's probably going to go to a civil engineer.
We go to a civil engineer, okay? And how is this one going to give you the answer?
I hope he knows.
Yeah, but he knows, so it means that he knows how to do it. So, and if you have to give him a hint, so how to do it?
I would consider it the inside and outside temperature as well as the insulation, number of windows.
Okay, so you are introducing, so what you will do in fact is use a model.
Do a
Okay.
Classic geometry for a building and then apply it.
Yeah, exactly. So it would be use a building simulation model. And here is introduced more or less all what is needed. So we need to know the materials in the walls, we need to know how much windows, we need to know the geometry, we need to know the sun, how the sun is going to influence, we need to know what is inside the buildings, okay? And this civil engineer or the architects, because they are all using the same kind of approach, will in fact do a simulation of the building. Okay? And to your opinion, what will be the difficulty that they will have?
Everything is going to vary with time.
First, yeah, but this is something that I need. So don't forget that I need the QBDT. T is a time. Okay, so there is a variation with time, for sure. But what is the other difficulty?
Maybe it's the way energy is supplied, depending on the utility you're going to use. There's some losses.
I think that this will not, because you are asking the heat load, so it means that they will not care about the way the heat is supplied, but they will have a difficulty for developing the model.
It's difficult to make a model for each building. Each building is different.
Why? Because each building is different, but okay, getting the size or the geometry of each of the building is not complicated.
Is it perhaps like the orientation of the buildings or maybe?
Yeah, but this is also something that is not difficult to solve. Okay, even if you go to Google Maps, you will see the orientations of the buildings.
What I mean is building an optimal orientation.
But let's say that, so in fact, you know that the whole Switzerland is available in 3D. So if you go to Swiss Topo, they are giving you the whole 3D map of Switzerland, including all the buildings. Okay, that means that the geometry part is not a problem. But I'm going back to your remark. So it means that the geometry is solved. But
Maybe buildings change throughout the year also, and renovations.
The consumption is not fixed. We cannot like know exactly what will be the consumption at a certain time. It changes every day.
every day,
Every day, every minute. Depends.
construction.
No, the consumption, the electricity.
Yeah, the consumption is going to change. So now, if we have to develop a model, it means that we have to identify what is in the model. So if you have, so let's go back to the architect that has to model the building. So what did he need? If we're talking about variations with time.
Maybe an initial condition, right?
I do agree. You need to know what is the initial condition. So and we will assume that everything is at 21 degrees C. And then what do you need? In order, why do you say that there are variations?
External temperature.
So you need meteorological data. Okay, so it means that you have to have a profile of the variations of temperature. Okay? And this is not so difficult to obtain. So Meteonorm, for example, is giving you, because they are measuring the external temperatures in a lot of places, so it means that it's easy to obtain an expected temperature profile throughout the year. Okay? So what is also varying in a building like this one?
Occupancy? Like who is using it, how many people?
Yeah, the number of people. So each one of us is radiating 100 watts. Okay, but we are around 60 here. Okay, so it's already 6 kilowatts of heat. Okay, and of course, if you are in the building, the lights will be on. Okay, and the computers will be plugged. And I'm going to use the beamer. Okay, so it means the presence of the people will be the other dimension which will be important. What will be also important, then they will justify the variations. Which explains why I'm not really offended by the fact that the windows are open now. It's the sun. So the solar irradiation is going also to influence the amount of heat in the building. Okay? But all those things are, let's say, easy to obtain. And what will be the major difficulty that the architect will be facing? The main difficulty that they will have is that they do not know what is the composition of the walls. Okay, we know the geometry, but do you know what is the content of what is inside this wall here? Do they have isolation materials or not? Okay, so what is the quality of the windows here? Is it double glazes, triple glazes? What is the material that is used here? Okay, which and they will in fact come back to you and say, okay, give me how the building has been constructed, and I will give you the amount of heat that is needed. Okay, so and then you will have a problem because he will send you. If you do not have the answer, then he will say, okay, but then I have to go in each of the building and measure things. It takes a lot of time, and I will send you the bill. So what would be the alternative then? Yeah.
If you know how much heat we put into the building, and then we can measure the temperature and reduce the losses.
This is exactly what we would the other option. So the first option was building simulation, but then we have a big questions about materials used, and otherwise we have referred to the heating system, and we make measures. Okay, so two big strategies, and so now I'm going to make a break, and then after the break I'm going to show you how we can make a link between the two, because the best would be to have nevertheless a model which represents what will be the energy consumptions of the buildings, but that is also able to assess the impact of improving the walls, for example, because I would like to optimize the system. Okay, so we are going to some extent to try to develop a model, but based on the measurements. Okay, so let's make a break and we start again. Unless if you have questions. If you do not have questions, then let's make a break, and then in let's say 10 minutes we are going to 15 minutes we are going to start.